Okay, well, this video is on solution stoichiometry, and we worked those practice problems today. And so I think that we need to go back and do a little review first, and then I'll work those problems. So we have molarity is the most common measure of concentration used in chemistry. And you have to remember that it is moles of solute per liter of solution. And so we represent that with an M or with square brackets. Both of those symbols mean moles per liter. When you are working problems, we do not use the capital M. You must use moles per liter, or else you will find yourself in a quandary because you will have things that don't make a lot of sense to you until you get a lot more practice than you're going to get in this course. So you're going to use moles per liter. I don't want to see you write the capital M in any problem whatsoever. It can only be used for your very, very final answer. You may see moles per liter written like this. That is legit. That means moles over liters to the -1, which is 1 over a liter, which is moles per liter. Okay, so red, it is 0.6 molar NaCl, means there are 0.6 moles of sodium chloride in exactly 1 liter of the solution. This particular solution, if you have 1 liter of it, you have exactly 0.6 moles. If you have, now solutions are evenly mixed, okay, so they're evenly mixed. So if you have 1/2 of a liter, you are going to have 0.3 moles of that solution, okay, of the sodium chloride in that amount of solution. So that is read as the 6 molar that you saw today. So it can also be written as this. That means the same thing as 0.6 moles of sodium chloride per liter of solution. So then there's this thing we call a stock solution, and a stock solution is what I get out of the stock room to make various solutions. So they are always the more concentrated one, and it is the one where the concentration is known. And so we often use these concentrated solutions to make a less concentrated form, or more dilute form is the right word for saying less concentrated, for general lab purposes. So it looks like this. If we were to take 50 milliliters of a 1 molar glucose solution and add distilled water, enough distilled water to make 100 milliliters, then we now have a 0.5 molar solution, because you started off a 1 molar solution with 50 milliliters in it has the same number of actual glucose molecules, moles of glucose, as this one does. You didn't destroy it, you just added water to it. So if you kind of want to think about looking at this, it would be more spread out, where you would have fewer glucose molecules and a drop of that solution, as opposed to a drop that should be like the same size, where you would see many more. But you're just taking the same number of moles, the same number of molecules, and diluting it with water, and this happens in mole proportion. So the number of moles of glucose before the dilution is still equal to the same number of moles after the dilution, but our concentration changes. Notice that you had 50 milliliters of a 1 molar solution. We add 50 milliliters of water, and now we have it's half as concentrated, so it is 0.5 molar glucose. All right, so the dilution formula looks like this. So taking a stock solution is, we usually write it as the first part, M1, so that's the molarity of solution 1 times the volume of solution 1 must be equal to the molarity of solution 2 times the volume of solution 2. So in this way, we figure out how to make solutions. So I would know, often the question is, for my stock solution, how much of this am I going to add to make some specific thing that I want? So they would tell me something specific they want. They would tell me the concentration of my stock, and then say, how much of this do I need to add to make this amount? So a problem might look like this. Why am I telling you this? Because this all directly relates to what you just did today. So an example of how to do this. So just the plain old dilution formula. What volume of a 16 molar nitric acid, very concentrated, very concentrated, the most concentrated nitric acid solution is needed to prepare 150 milliliters of a 0.1 molar nitric solution? So you could never ever have this out in the lab. That would be extremely dangerous. But we often have that molarity. So how do you make that? Well, you take, this is your stock, what you know about it. It's 16 moles per liter, and you are asked for the volume of that stock solution that you are going to need to make a 0.1 molar solution. And how much of that do you need? 150 milliliters. So if you notice, I can, when I do the math, I would take and divide this side by the 16 moles per liter, and these moles are going to cancel with these moles, and this liter, or one of the liters, cancels with this one. Denominator, if I flip it around, it's going to cancel with this one. It's going to tell me the liters. That part may not be right, but I come up with liters. So if you wrote it all out, you would see that. So 0.00094 liters is what I need. That's not a very useful unit for me. I need something more in milliliters because I have graduated cylinders that measure in milliliters. I also have very accurate, you'll remember from the lab, those volumetric pipettes and those graduated pipettes that can do this accurately. And you should also remember that we would always make this in a volumetric flask that has exactly one line across the top. So, but these come in whole numbers usually. Well, I don't know, you can get them in different numbers, but if this is what you were going to do, then this would be a 0.15 liter volumetric flask. Okay, so we'll get back more into that, but to do your empirical formula lab, you have to know how to make a solution, and so this is very important information for you because that's coming up really quick. So we'll talk a little bit more about that. But anyway, so we want to add the 0.94 milliliters of this very concentrated nitric acid to enough water, and we ought to do what we ought to add acid to the water, so we want 150 milliliters. So we would put about 100 milliliters, and then we would very carefully and very slowly add the acid. So this would be your water, not full. That mark would give you this much. And then you would add the acid. So then you add acid, slowly, and swirl until you get your acid, and then you finish filling it to the final drop at 0.15 liters. So that's how you make a solution. So now we can undo that and figure out how many moles of a substance, because that's what you were asked for today. For the most part, you were given these molarities and volumes, and a volume of this, and you were asked for the molarity, or you had to know the number of moles that you were putting in to some reaction. So you can use this formula. This is also the same as regular Stoich. This is just cleaner, faster. Okay, so when we mix two solutions together, That is code word for dilution. Mixing two solutions together is code for a dilution. Why? Because both of them must come out less concentrated than they went in. So, and in this case, the volume that is new. You're going to have a new and different volume because you're adding two solutions together. So if you look at this diagram, we have this much of potassium bromide. So this is potassium bromide. Potassium, I needed a pen. Thank you. Potassium bromide. And this is soluble. So notice that this is potassium floating around. This is bromine floating around. The water molecules are not shown for clarity. Over here, we have a sodium chloride solution, where because these are always soluble. Why? Because of that and because of that. So when you have an aqueous solution, you're never going to find it as a solid. They will all be suspended, floating around as little bitty ions, and no, you cannot see them. They are way too tiny. So these solutions look colorless, clear, colorless, transparent. Okay, so then, but if we put these two together, notice that this volume has to add to this volume. So if we had, let's say that is 0.5, let's just make up a number, 0.5 liters of a 1 molar solution of potassium bromide, then if I have 0.5 of a 1 molar solution, that would be 1 molar solution, then I would know that if it's a 1 molar solution, then I have 1 mole of this potassium bromide in every 1 liter. If I have a half a liter, I have a half a mole of the potassium bromide. So I have just added, this is 0.5 moles in 0.5 liters. Same thing over here. We've got 0.5 liters of a 1 molar solution, which means I have 0.5 liters and 0.5 moles. Now, what does that really mean? That means I have 0.5 moles of potassium over here I have sodium ions, and I have 0.5 moles of chlorine ions. Over here I have 0.5 moles of potassium ions and 0.5 moles of bromine ions. Okay, so when I add all this together, I now have, I have 0.5 moles of K, 0.5 moles of Br, 0.5 moles of Na+, and 0.5 moles of Cl-. All in, now I have 1 liter of solution. I added a half a liter and a half a liter, and now I have all of those things in 1 liter. So now what's my new concentration? Because my concentration changed because I added these two things together, therefore they are more dilute. I have 1 mole of sodium ions sitting in 1 liter of solution. 1 liter of my solution. So what is that concentration now? What is the concentration of the sodium ion? Well, it's 0.5 moles per liter. What was it before? I showed you the concentration of the other. Over here, you add 0.5 moles in a half a liter, right? So let's compare. So the before, so this is before, 0.5 moles of that Na sodium ion, and we had 0.5 liters. So we had a 1 mole per liter of Na plus in every liter of that solution. Or it could be written as 1, because I'm at the end, 1 Na plus, 1 molar Na plus. So you see how it dilutes that down. And that's the crux of some of the problems that you were working today, because you compare this one to this one and you see that it changes, all right? So sometimes they'll do the tricky thing and they'll give you something like, to one of them today said K2CR 207 potassium dichromate. And so what you have to know is that for every one of these moles, I have 2 moles of potassium, so it's going to produce 2 times as much, 2 times the moles of potassium ions as moles of the compound. So you just have to kind of put that under your hat and keep that there. Okay, so now, I don't know what I did, I messed that up. There we go. So just be sure that you are doing 2 things. You have to keep track of your total volume, because you have to take whatever your interest is, typically some ion, so you have your moles of ion and your total volume of solution, all right? And these can come from different places, as we saw today. So this could have been, if I just erase this, I'm moving on, I'm going to hurry. But I just wanted to show you what this would look like if we pretended that this this is one of your problems from today. If you pretended that this was, let's say, Na plus and Br minus, then you would be adding a source of Na here and a source of the sodium ions from here and a source of the sodium ions for there. So these would be additive. So if I had 0.5 moles here and 0.5 moles from here, I would have 1 whole mole of sodium ions in my new solution, okay? All right, so neutralization, so I was asked today about this. So because dilution formulas are a simple way to get to mole-to-mole ratio, and that's the way our reactions happen, and because neutralization reactions, that's acid-base reactions, are always an aqueous solution. You cannot have an acid or a base unless it is an aqueous solution. And so we can use a modified form of the dilution formula, but it must be modified or AP will not give you that point. If you put a 1 down here and 1 down here and a 2 and a 2, they're going to say nope, no point. But this works. Now, they don't particularly like it when you do that. You can use it, you can, but you don't necessarily have to call it that. You can just multiply your moles times your volume. So never, ever, 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 ever forget that molarity times volume gives you moles. Always. It's always going to give you moles. Why? Mole per liter times a liter equals moles. That's what you're left with. So always remember that. That is a trick to get you to moles and on your way to working a problem when you get stuck. Okay, so this N, so this is the moles of the molarity of the acid times the volume of the acid must be equal, if it is completely neutralized, must be equal to the molarity of the base times the volume of the base. But when you're doing these calculations, you must keep in mind that we don't always get a 1-to-1, and so we have to use that N there, where N represents the number of moles of hydrogen that you get from your acid per molecule of acid, and this would be the number of moles of I don't know what that's doing. Moles of hydroxide ion that you would get per mole of base. I don't know, I managed to mess that up. But so if you're looking at, always be, you had this was one of the problems today. So you have something like H2SO4, and then you're adding this to NaOH. Okay, well, this wasn't the problem yet today, but you get 2 moles of hydrogen, and you get 1 mole of OH minus. So you have to use 2 of these for every 1 of those. So I need to say that I'm going to need, this is the moles, I get 2 for every 1 of those. But what do I need to double? I need to double this one right here. You just have to use common sense to know that and think about your molar ratios, all right? So if you balance this equation, you're going to have a coefficient right here. That's going to be 2 of that. So we're going to get Na2SO4 plus H2O, and to balance it, I am going to need 2 sodiums. So there's my 2 sodiums. Well, here's my 2 waters now. It's balanced. I have to take this coefficient and put it right here. All right? So when I get finished finding out the moles I need or whatever, I have to multiply it by 2. So let's go get to those problems. Okay, I'm going to pause and then set this up bigger. Okay, so now you get the warning. That is the dilution formula, but it's all Stoic, and you don't always use the dilution formula to get you where you need to go. It is handy for some things, it is not for others, but it gives you an idea of where to start, I hope. But anyway, this problem says a 0.1 molar no, it says 70 point. Now, what does this dot mean? That dot means that, why won't it let me have a, there. That period means this is significant. 70 milliliters of a 3 molar sodium carbonate is added to code for new volume, code for dilution, is added to 30, again, that's significant, milliliters of a 1 molar solution of sodium bicarbonate. What is the resulting sodium ion concentration? So, I need to know moles of sodium ion, total moles of sodium ion, and my total new volume. Okay, so how am I going to get that? Well, I have 70 milliliters, which is going to be 0.07 liters times that 3 mole per liter solution, and that is Na2CO3. But now, how many sodium ions am I getting out of that? Well, I'm getting 2 moles of the sodium ion. So let's see, we have 0.21 moles of Na2CO3 times the 2 moles of sodium ions that occur in every 1 mole of the Na2CO3. So I have a total of 0.42 moles of sodium ions that I'm adding from this. So from this solution, from this one, I have 0.42 moles of Na+. And how much was that? 70 milliliters or 0.07 liters. And then from the other solution, plus, I have 0.03 liters of a 1 molar solution, 1 mole per liter solution. And so that's going to give me 0.03 moles. And this is a 1 for 1, so I have that many moles of NaHCO3 I'm dumping in. And it's a 1-to-1. For every 1 mole of the NaHCO3, I get 1 mole of Na+. Therefore, I'm getting 0.03 moles of Na+ from this side. So 0.03 moles of Na+. And then how much of that solution, I have to remember it's my total volume, so I'm going to have to add it all together. It was 30 milliliters, so 0.3 liters. And so altogether, I'm going to have 0.45 moles in a 0.1 liter solution. So that means it's going to be that means it's going to be a 4.5 moles. This is Na+, moles per liter, Na+, or moles per liter. Can you read that? Let's see. Moles per liter, Na+. And then you find it up here, and your answer is D. Okay? Most of the rest of these are the same song, second verse.